Okay, so the next talk will be given by Max Zeuner. It's a joint talk with Carlo, again, on Anders, on representation independence via the cubical structure identity principle. So you can go.
Yeah, thanks for the nice introduction. So this is going to be sort of the second talk of Carlo's session. And yeah, this is work we've been doing with Anders. So the idea is use the tools of cubical type theory or univalent foundations to apply it to problems in computer science. So let's start with an example. So imagine we're a programmer and we want to program in Cubical actor. So this is really the cubical part of our talk. Everything is formalized in Cubical actor, and we want to program. We have some type A that we're going to use, and we want to use multisets or finite multisets over A. The nice way in Agda to implement a minimal multiset signature, multiset interface is using records, and then we have an implementation of multisets, some carrier type T. This has an empty multiset, an insert function for adding new elements of A to a multiset, and then a count function that counts the multiplicity of elements of A in our multisets. Usually we also want further laws or axioms, which we're going to ignore here. So for example, we want our carrier type to be an H set, or we want, I guess, like pretty common laws, but for now we just have 3 components. So then our program is some computation that takes a type T, a multiset structure on T, and gives us a natural number. And in particular, since this multiset structure is a variable, our computation type checks for any multiset implementation whatsoever. But if we want to get the actual number, we of course have to apply it to concrete implementation. So here's an implementation, rather straightforward one. For now, whenever we talk about multisets over A, we assume A to be a discrete type, meaning it has decidable equality. And if we have that, we can implement finite multisets using list of A as a carrier type. Empty multiset will just be the empty list. Inserting will just be appending to the list. And then we have a count function that sort of traverses the list, checks if an element X is equal to A. So this is where the decidable equality comes in. And then if that's the case, we increase the count by 1. Otherwise, we just go further down the list. It's a bit inconvenient because then our multisets get pretty long strings that has like each element occurring with the multiplicity. So maybe a more compact presentation is implementing it as so-called association lists. And here the carrier type is list of pairs of elements of A, and then second component is the multiplicity occurring explicitly. And we kind of a bit more thoughtful about the insert function, which means we traverse the list if we encounter, if we want to insert A and we encounter it, some equal element, we raise the multiplicity. Otherwise, we just go further down the list. And then if we count the multiplicities, we just add them as we go along. So the question, and this is really at the heart of the problem of representation independence, is how do we know that the computation will give the same result when applied to either implementation? And well, so what we really want is proof that computation of applied to list implementation and equals computation applied to the association list implementation. Well, in computer science, they've got several approaches to ensure that, looking at the relation that these 2 implementations share, and well, this is what parametricity theorems can do. But what we want to do here is look at the tools that we get from homotopy type theory and univalent foundations. And in particular, we want to see when we can turn the relation between the two implementations to an equality, because that, of course, ensures representation independence. So, well, the most important tool, of course, to get equalities is the univalence axiom, or in cubical type theory, rather, the univalence theorem. That alone won't do it, because we can just apply it to the carrier types, so lists or lists of pairs in our example. But of course, we have to take into account the additional structure. Let's make this concrete. So if our basic type A was n, then n is equivalent to n times n. So this is the classical bijection we learn as undergrad students. And then we get that list of n is equivalent to list of pairs of natural numbers. But that, of course, will be an equivalence that doesn't preserve the multiset structure. In particular, the second component is supposed to tell us something about the multiplicity, and that won't be respected. So what we need is, in fact, the structure identity principle that allows us to identify isomorphic structures. But, well, in this case, things are a bit complicated. We have a structure preserving map between our two multiset implementations. We have a map from lists to association lists that just adds elements with multiplicity 1. But this won't be an equivalence. In particular, any association list that has list terms with multiplicity bigger than 1 won't be in the image of this map. And sort of to make things even worse, we're concerned with what is called a many-to-many correspondence. So take the following multisets, 2 of them live in list A, 2 of them live in the association list type, and sort of they all represent the same finite multiset, really, namely the one containing x twice and y twice. So what we can do, though, is use higher inductive types, sort of quotienting lists and association lists by the right relations to make them isomorphic. We can also try to be a bit more systematic, and this is what we'll do here as well, using so-called Zig-Zag-Complete Relations. But before we can look at how this works, a quick overview of the structure identity principle as it is in the Cubical actor library. So this is a variation of Martin Escardo's structure identity principle that you can find in his actor lecture notes. And so we really follow his version when it comes on how to describe structures and so on. A few things are a bit more cubical. We use, of course, path types here. But basically what a structure is a function on the universe type. So, of course, actor users might be more used to set, but in the cubical actor, it's renamed to type. I guess that's pretty appropriate. Also, structures can be universe polymorphic, but we want to keep it simple in this talk. So our record from the very beginning is finite multiset is such a structure. It takes a carrier type, returns this record that has this additional structure, and then the type of S structures or multiset structures is the sigma having a carrier type and the structure defined on it. But we need a bit more. We need to have a notion of structure preserving at least equivalences. And what this is, a notion of S structure preserving equivalence, is a iota that takes as input 2 structure types or types with the structure, and it looks at the equivalence of the carrier types and gives us back a new type that we can read as the type of proofs that this equivalence is structure preserving. So I'm not going to spell out what the iota for finite multisets will be, but I guess you can all figure it out yourself. It should preserve all the structural components in the obvious and appropriate way. So it should map the empty set to the empty set, should commute with insert, and respect the count function. And then the type of structure preserving equivalences is again just this sigma of equivalences of the carrier type, such that we have a proof in this iota. Note that this iota doesn't have to be a proposition. So in particular, we want to define when such a pair S and iota is well behaved, so that we can apply the structure identity principle to these structures. And that's what we call a univalent structure. Univalent structures says that whenever we have structure types and an equivalence of the carrier types, then this iota is actually equivalent to this dependent path type, which won't be a proposition in general. And notice that Martin has in his lecture notes slightly different definition of what he calls a standard notion of structure, but it's essentially equivalent. Here we just use the cubical primitives for convenience and the univalence term. And then we can state the structure identity principle, saying that whenever we have a univalent structure, then the type of isomorphisms for any two structure types, for any two structures, is equivalent to the path type. And this is the path type in the sigma type that is type with structure. So of course, the bottleneck of applying the SIP is showing that the structures we look at are univalent structures. But this is one of the big conveniences of Martin's formalization, that we can split these proofs up. We only have to prove it separately for the different components. So in our multiset example, empty set, insert, and count. We could also, if we had added proposition valued axioms or laws, we could have ignored them as well. So this is actually pretty feasible. And now we can solve the problem of representation independence by adding paths to our implementations. Because remember, we don't have isomorphic implementations which we need for the SIP. Here's a way to define list-based finite multisets as a hit due to Chudhuri and Fiore. It's been around in the Cubical actor library for a while. And basically, we have the list constructors and then add a path com that allows us to swap elements in our multisets. And then also we set truncated, says several advantages. But now we can prove that this count function that we had for lists, which is how the count function should act for these constructors, respects the com constructor in a way, sort of it's invariant under swapping elements, and thus we get a FM set count function and a multiset structure on FM set. We can also prove, and this is actually not so straightforward, that just adding this constructor com is sort of enough. We can prove count extensionality from that. Giving two finite multisets or two FM sets, then if they have the same multiplicity for each element A, then they're already path equal in FM set. So this already shows us that we are on the right track here. This is what we want. And we can do something similar for association lists. Now we actually have to add a bunch of constructors. So we have the usual constructors, and then we have a constructor path constructor that allows us to swap elements, to add multiplicities when the same element occurs multiple times, and delete elements of multiplicity 0. This again, we can show that this inherits the multiset structure from our previous association list implementation, and now we get an equivalence between those two types that respects the multiset structures. So we get representation independence for these two implementations. So I think it's a good point to step back a bit and look at what we have achieved. So what we did is we started with the many-to-many correspondence that that wasn't isomorphic. We turned it into isomorphic implementation using hits, and then now we are in the position to apply the SIP. We also proved count extensionality, which sort of tells us that we really got what we wanted, unique ways of representing finite multisets in these hits up to path, and we can transport this proof of count extensionality to this hit ASOC list. This is also quite nice because proving this directly for ASOC list would be a bit of a pain because of the many path constructors. However, one thing that might one concern that might be raised is that this solution does not really scale. So it's very specific to the multiset setting and the two implementations. Maybe one could criticize that we got kind of lucky by guessing the right higher constructors, the right paths to add for the hits. So how can we make this work for more many-to-many correspondences? So if we want to do that, we have to adapt a somewhat relational approach, and the basic ingredient is the notion of a zigzag-complete relation. So given two types A and B, we have a relation on A and B. We want this relation to be proposition valued, and then we say that R is zigzag complete if the following picture holds. If we have two terms A and A prime in A, B and B prime in B, such that A is related to B, A prime to B, A prime to B prime, so sort of we have this zigzag scheme, then we get also this dashed relation. We get the zigzag in the other way around. And such a zigzag complete relation is called a quasi-equivalence if we have functions between A and B, forward and backward, such that each A is related to its image on the forward and each B is related to its image on the backward. And with that, we can define new relations on A and B respectively, sort of R left and RB, that relates elements A0, A1, if A0 is related to forward of A1, and similar for B. And this is the result that we get and that we will use. If we have a quasi-equivalence relation, then we get equivalence relation, proposition valued equivalence relations, R left, R right. And we can look at the set quotients, R quotiented by R left, B quotiented by R right. And we get an equivalence induced by these maps backward and forward. So they are well defined on the quotients and are mutually inverse on the quotients. And yeah, then applying this to the multiset setting, again, we have a discrete type A. We pick the zigzag complete relation that relates a list and an association list if they give the same count, if they contain the same elements with the same multiplicity. I guess it's not too hard to believe that this is a zigzag complete relation, and the forward and backward functions to make this into a quasi-equivalence relation are pretty straightforward to find as well. So this is the map that we already saw. The backward map is not too surprising either, I guess. And this really defines a quasi-equivalence relation. This is not too hard to prove. So what we get is an equivalence of these set quotients, but moreover, the particular way we picked our quasi-equivalence relation allows us to get an induced multiset structure on the two quotients. And the equivalence that we get from forward and backward is a multiset isomorphism. One more nice thing to say is that I keep tapping on my touchpad. One more nice thing is that that these these relations are left or right really relate lists or association lists if they are count extensional. So we get count extensionality for free, really. So that's a nice feature compared to the direct hit approach. But putting everything together, the picture that we sort of get is that we have proved count extensionality for FM set. This gives us an isomorphism here, and we already established these horizontal isomorphisms. So what we really get, of course, we can compose all these isomorphisms to get one here. We really get is a commuting square of isomorphic multiset implementations, and we sort of get representation independence for all of those 4 implementations. Note that this, of course, depends on us being able to choose R forward and backward in the nice way we did. So this is really like we would like to generalize that, formulate and prove a relational SIP that gives us conditions on when such a quasi-equivalence relation allows us to use this whole machinery to get representation independence or make the SIP applicable. And of course, we'd like to have more applications. Would also be interesting to see how this relates to parametricity, and then maybe have some more have some of the proofs involved that actually concern the SIP, have them automated. So this is all joint work with Evan Cavallo right now. Yeah, and that's it for me. Thanks.
So there is already a question in the chat. I don't know if you can see it.
Yeah,
otherwise,
let me open the chat. Carlo. No, wait.
Virgo.
Is list structurally the same as list with permutation part? So I guess this concerns the vertical arrow here, right? Yeah, it is actually. So the point is to just define the map from here to here. We have to already use count extensionality, but then prove that this preserves the multiset structure isn't hard, because basically on the list part, on the non-higher constructors, so set quotients are of course a hit in the cubical actor as well. On the non-higher constructors, they both behave exactly like the list implementation that we had in the very beginning. Yeah, but thanks for the question.
So does it answer your question? Yeah. Yes, I think so.
Yeah, I guess my question is more like the same way that we can see a difference between list and association lists. If I were to use those glasses and look at list of A quotiented by R to the right, would that give me the same as the FM set representation? So I'm talking about a way where, just the fact, I mean, of course, all these types are going to be equivalent, but I mean, the representation, is it the same that we get this way?
Say it again. I think what do you mean by the representation is the same?
Well, what I mean is that, okay, so you had originally, right, at the start, you had list of A and you had an association list as 2 representations, right? And you said that we can see that there's an operational difference between the 2, because the list of A one is just gonna keep growing.
Yes.
Now, of course, this is the kind of difference that you can't really see if you only look at things extensionally, right?
Yes.
So I guess my question is that the type that you get by quotienting list of A with this R to the right relation.
Mm-hmm.
Right? So is that the same as the FM set type, which was a list type plus the permutation path constructor?
Yeah. Well,
which is still going to be just a list, right? So it is going to be represented operationally as just a list. The path constructors are not really going to change anything in that, right?
yeah. Well, I mean, if you program with these hits, of course, you always have to take care of these path constructors and say how they act and stuff. But I guess your point is like representation of multisets in these types in practice won't become much shorter, right? Is that what you're going at?
Right. Yeah, I guess.
Yeah.
Yeah. So I guess what I'm asking is whether we have fully recovered FM set exactly, or we got something that is not necessarily including new path constructors for permutation, but maybe something else. We can't really be sure because we didn't really write R to the right. We wrote R and then we computed R to the right from it.
Yes. Well, I mean, you can actually write, yeah, but yes. So what is the question then?
So maybe we can, there are other questions. So,
Yeah.
So there is no coffee break for you to suggest to speak offline, but maybe by mail, I don't know.
Yeah, we can.
So
Discuss
there was a
this
question by Andy Pitts, but which was answered by Carlo about
Yes.
the history of zigzag relations. So maybe we can skip it, or is there something more to say about it? So it's
we'll have to read the chat first.
and, okay, I feel that the chat is answering the question.
Okay.
Somehow. So I could. There is another question by Vikraman Choudhury.
Yeah.
Do you have a figure for the first point in your last slide?
So that's the point. Formulate and prove a relational SIP. Yeah, there's been some progress on that, and we'll hope to have that in a paper with Evan soon. I don't know if there's, yeah, maybe we can talk about that. You can mail us or something if you're interested, I guess. Not sure how much time we have left. But, yeah, so again, the trick is talk about what about relational structures and relational structure equivalences and stuff. Carry all that over to relations and then prove a similar version of the SIP, really. Yeah.
So finally, I feel that all questions are answered. Or is there someone more? So I guess we can thank you again.
Thanks.
And okay, Chris and Benedict, that's okay like this.